a second-year PhD student working in the NAFEL group. My work is supervised by Jean-Jacques Greffet and François Marquier, and it's supported by the French DGA and the CNRS. And in this talk, I will discuss the design of highly efficient optical antennas with insights towards fabricability. So first, the concept of antenna can be applied to optical waves in an emission process. When putting an antenna in the near field of an emitter, a small emitter, the size, shape, and materials of the antenna can be designed in such a way that it couples efficiently to propagative waves. Let's first address the rate issue. So when computing the average emitted power of a dipole, one can deduce an acceleration of spontaneous emission, a factor of an enhancement factor, which is proportional to the imaginary part of the scalar product between the dipole, the electric dipole moment P, with the electric field E at the position of the dipole. And so to understand this equation, let's consider a one-dimension cavity, which is constituted of a perfect mirror and a mirror that can transmit a part of the energy. So a standing wave may exist for some thickness of this cavity. And when putting a dipole at an antinode, at a node of this mode, it cannot couple to this mode. And so this equation tells us that we can inhibit the emission, the spontaneous emission of this dipole. Then when putting the dipole at an antinode of the mode, one can increase the spontaneous emission. Then by conservation of the energy stored, by reducing the volume cavity, one can increase the electric field. And so an increase with the confinement will result in an increase of the emitted power. But there's a limit to this confinement, which is given by the existence of a standing wave, which is half the wavelength. And so to further increase the emitted power, one needs to reduce the loss of the cavity, which means also to increase the number of photons stored. And to do so, one needs to decrease the transmission of the second mirror, which also leads to an increase with the quality factor. And from all those observations, in 1946, Edward Purcell found the exact formula of the enhancement factor of spontaneous emission for a single mode cavity. And this factor is proportional to the product of the cube of the wavelength with the quality factor and with the confinement of the mode. Then for dielectric cavities, because of the standing wave issue, the effective volume of this mode cannot be less than half the wavelength cube. So this leads to a maximum value of the Purcell factor, which is roughly given by the quality factor. So to cope with this issue, one may use plasmonics to further increase the confinement. If one puts a dielectric metal interface in the near field of a dipole, it can excite surface waves called surface plasmon polaritons. So the electric field of a surface plasmon mode decreases exponentially and with a typical length of a few nanometers in the dielectric. And those surface waves have a higher wave vector than the one of propagative modes in the bulk of the dielectric, which means that we need to use some tricks to couple two plasmonic modes. And it works for a dipole close to the interface, because in the near field of the dipole, the near field of the dipole can be seen as a sum of evanescent waves with very high wave vectors. The match of wave vectors can apply. So then, by putting a thin metallic layer on top of the dielectric layer, one can create a highly subwavelength cavity. And furthermore, the usual factor of quality factor of plasmonic cavities is in the order of 10, which provides broadband operations. So when structuring the metallic layer, using, for instance, the shape of a disk, a plasmonic mode can propagate radially and be reflected by the effective boundaries of the cavity, bouncing over and over. And for some specific diameters of the disk, a standing wave may take place. And so when computing the cross-section electric field, a radial cross-section of the electric field, one finds this standing wave, which is given by a sum of Bessel function because of the cylindrical symmetry. Then this distribution, this electric distribution, will generate a current density in the disk that will radiate to the far field. And moreover, by diffraction, the size of the disk controls the directivity. And we call those cavities the patch antennas. And to conclude, we get a spontaneous emission that is enhanced 100 times. 99% of the single photons emitted are collected in a numerical aperture of 0.85. It provides broadband performances, and 75% of the photons, 75% of the emitted power will go into single photons, and all those performances are robust with any deviation with the geometrical parameters, which leads to a possible fabricability. Thank you for your attention.